Welcome back, focused learners. I'm absolutely thrilled to have you here for this explainer because today we are tearing up those flat, two-dimensional drawings of molecules you probably remember from a high school textbook. We're replacing them with reality. You see, the truth is, molecules are not just flat sketches on a chalkboard. They are highly dynamic, three-dimensional architectures. Every single substance in the universe, from the water we drink to the DNA right there in our cells, has a highly specific 3D shape. And today, we're going to learn exactly how to build those shapes from the ground up.
Okay, let's dive right into this. Here's our roadmap for today. First, we'll cover the rules of repulsion. Second, linear and planar architectures. Third, we'll look at the tetrahedral family. And finally, expanding the grid.
Take a look at this. This master table right here is basically your ultimate architectural blueprint. This single grid holds the key to predicting the three-dimensional shape of almost any molecule you'll ever encounter. By simply counting the electron groups, the bonding groups, and the lone pairs, which you can see laid out in those first three columns, you can accurately map out the invisible forces that shape our physical world. We're going to be referring back to this map throughout our entire journey today.
All right, Section 1, the rules of repulsion. We're looking at the blueprint versus reality.
So it all boils down to one acronym, VSEPR. That stands for Valence Shell Electron Pair Repulsion Theory. Now the crucial point is right there in the name. We're talking about the valence shell, the outermost electron layer of the atom. The inner electrons, they don't really dictate the shape. It's these outer ones doing all the heavy lifting. Now electrons are negatively charged, and as we know from basic physics, like charges repel, right? So the electron groups surrounding the central atom of a molecule absolutely hate being near each other. To find peace and stability, they literally shove each other out of the way to maximize their distance in three-dimensional space. That single, simple act of repulsion is the driving force behind all molecular architecture.
Now, to really master VSEPR theory, you have to understand the difference between these two geometries. Think of electron geometry like the unseen foundation of a house. It includes absolutely everything taking up space around that central atom, both the visible structural beams, which are our bonding groups, and the invisible space takers, which we call non-bonding lone pairs. Molecular geometry, on the other hand, well, that's the physical reality. It's the visible house that actually gets built on that foundation, taking into account only the atoms that are physically bonded together. Trust me, distinguishing between these two is the biggest secret to mastering molecular shapes.
Moving on to Section 2, Linear and Planar Architectures, the Perfect Shapes, and the First Twist. Okay, imagine a central atom has just two electron groups and zero lone pairs. The absolute furthest they can possibly get from each other is on completely opposite sides, right? This creates a beautifully perfect linear geometry with a 180-degree bond angle. Think of carbon disulfide, where rigid double bonds lock it perfectly flat and straight. Step up to 3 electron groups, and we get a molecule like boron trichloride spreading out perfectly flat with 120-degree angles between each chlorine atom. It kind of looks like a peace sign. It's just logical perfection.
But what's really interesting about this slide is the plot twist. The twist arrives the second we introduce a lone pair. Look at that 3-group system again. If one of those 3 groups is a lone pair of electrons instead of a bonded atom, the molecular reality completely changes. Take SO2, sulfur dioxide. You might know it as a major pungent component of volcanic smog. Its electron blueprint is trigonal planar, but because one position is occupied by an invisible lone pair, the physical molecule looks completely bent. And here's the kicker. That unseen lone pair is actually slightly more repulsive than a bonded pair. It acts as an invisible shaper, forcibly pushing the oxygen atoms away from itself and squeezing that perfect 120-degree bond angle down to something less than 120 degrees.
Which brings us to Section 3, the tetrahedral family. Meet the invisible space takers.
So, all 3 of these molecules share the exact same foundation, a 4-group electron geometry called tetrahedral. But the resulting physical realities? They're wildly different. With 0 lone pairs, we get methane, CH4, the primary component of natural gas. Swap in 1 lone pair, and we get phosphine, PH3, a highly toxic gas. Swap in 2 lone pairs, and we get hydrogen sulfide, H2S, famously known for smelling like rotten eggs. Because the number of invisible space takers changes, the geometry is fundamentally muted. I really want you to burn this number into your memory. 109.5 degrees. This is the absolute gold standard angle for a perfect, symmetrical, four-group tetrahedral shape in 3 dimensions. In our methane molecule, CH4, all 4 hydrogen atoms spread out into a perfect 3D pyramid with a triangular base, perfectly balancing the repulsion at exactly 109.5 degrees apart.
But watch what happens energetically when we start adding those lone pairs. I like to call this the squeeze. In pH3, we swap one bonded atom for a lone pair. Now, because that lone pair is held by only one central nucleus, rather than being shared between 2, its electron cloud bulges out wider. It's greedy for space. It heavily repels the 3 remaining bonds and squeezes them together to less than 109.5 degrees. The shape is no longer tetrahedral, it's now a trigonal pyramidal shape. Now take it a step further with H2S. We have 2 lone pairs. These 2 invisible space takers push against each other and violently crush the remaining 2 bonded hydrogen atoms tightly together, plunging the angle way below 109.5 degrees. The result is a highly compressed, tightly bent shape.
All right, let's step it up. Section 4, expanding the grid. We're talking complex symmetries and some truly wild shapes.
Let's look at the 5-group family. This is a real game changer because for the first time, we have 2 different perfect angles coexisting in the same blueprint. The base shape here is trigonal bipyramidal. Take phosphorus pentachloride, PCl5. It exists in reality as this pale, greenish-yellow solid, and it perfectly demonstrates this dual angle setup. Imagine a flat triangle of atoms around the middle. We call those equatorial, and they sit 120 degrees apart. Then imagine 2 more atoms poking straight up and straight down. We call those axial, and they sit at a 90-degree angle to the flat triangle. This dual angle setup is a recipe for some amazing transformations.
And this brilliantly illustrates how VSEPR rules dictate structural mutation step by step. Starting with the perfect PCl5, we add 1 lone pair to get SF4. The lone pair prefers the roomy 120-degree equatorial positions, squeezing the remaining atoms into an asymmetrical seesaw shape. Both the 120 and 90-degree angles get compressed. Add a second lone pair for ClF3, and the repulsion violently bends the molecule into a rigid, sharp T-shaped architecture with angles strictly less than 90 degrees. But the grand finale is XeF2. We add a third lone pair. Xenon is a noble gas, which normally refuses to react with anything, but when it's forced to bond with highly reactive fluorine, we get this bizarre structure. All 3 lone pairs crowd the equatorial plane. To escape the intense repulsion of those 3 electron clouds, the 2 remaining atoms flee to the extreme top and bottom axial positions, astonishingly forcing the 5-group molecule back into a perfectly straight, symmetrical, linear 180-degree line. It's just an incredible full circle.
Let's move to the heavyweights and see how this builds in the massive 6-group family. Our baseline, with 0 lone pairs, is the octahedral geometry. Think of sulfur hexafluoride, SF6. It's an incredibly dense, heavy gas purely because of this perfectly uniform octahedral grid locking the atoms rigidly in place. Every single bond is exactly 90 degrees apart, it's structural harmony. But watch the 3-step transformation. Step 2, we introduce 1 invisible lone pair to make BRF5. That lone pair pushes all the remaining bonded atoms upward, forcing them into a square pyramidal shape and shrinking all the angles to less than 90 degrees. But then, step 3, we add a second lone pair to make XeF4. The 2 highly repulsive lone pairs want to get as far away from each other as physically possible, so they position themselves at the exact top and bottom of the molecule. Their repulsion perfectly cancels each other out, snapping the 4 remaining atoms back onto a completely flat, perfectly symmetrical square planar 90-degree grid. The balance of forces here is truly elegant.
As we wrap up this explainer, I really want to leave you with this final thought. Everything we just explored, the linear bends, the tetrahedral squeezes, the seesaws, and the perfect grids, it's all driven entirely by the simple, unseen repulsion of electrons just trying to find their space. If this invisible architecture dictates the exact 3D shape of a simple gas molecule with absolute precision, just imagine how these exact same rules scale up. How does this invisible force dictate the twisting ladder of our DNA, the folding of complex proteins, or the precise way a life-saving drug binds to a cell? By mastering these microscopic rules of repulsion today, you have literally just unlocked the foundational structural secrets of the entire biological and chemical universe. Keep questioning, keep learning, and I'll see you in the next explainer.